In this lesson, we are going to translate intervals into relevant values, follow the process of translating intervals into relevant values, and appreciate the significance of translating intervals into relevant values. In our last lesson, we learned about mapping continuous random variables. To understand the function, we said that we must make a separation between the definition of the function and the target items of the function. So after that we computed the integral, we learned that this reflects the subset. The measure of any dx interval is equal to dx. We learned mapping a continuous random value can properly mimic the underlying reality. So if you miss lesson number 13, the link is given in the description below, because learning lesson number 14 is more meaningful when you know lesson number 13. We will learn about transforming values beyond calculus. In some cases, the normalization fails. So we talked about some normalization methods. So in our last lesson, we studied how to normalize a certain value. So in some cases, however, normalization method may fail. It's because some prerequisite calculus technicalities cannot be applied. So let's remember that we are considering length or magnitude in continuous distribution. So with that, we said that that could not be negative. That could not be less than 0 because length can never be less than 0. Okay, remember that. So to understand what I mean, let's have this problem. Supposing we do have x and y, variables x and y, that are uniformly distributed in a certain interval. And this interval is defined as, so we have a z, x over y minus x. So still remember before when we talked about the density function of a normal distribution. Okay, so this one, and we said that the area is always equal to 1. That is from the point of origin to the last point. Okay, so if you missed that, the link is given in the description below. So we have this one, and so for example, when we say, just to show you, z, and you're going to find the function of z, this actually fails. Okay, this fails. So maybe you would like to ask me, why does this one fails? Of course, remember that, again, we are talking here of magnitude and length, and we say that when we talk about magnitude or length, that can never be going to the left of this plane or going to this, because it is always positive, and that is length. Okay? So, however, in this case, let's consider that z is, although this is not, z does not belong to -1 and 0, but let's think that this is possible, that it's possible that x and y could have a different signs, which is -1 and 0. So given that x and y are uniformly distributed over 1 and 0, so let me write that one here, 1 and 0. So remember that this is the one that we talked before, that the value of x and y would always be between 0 and 1. But let's just assume that our case now is like this. Okay, and not this one. So we mean to say that z is greater than 0. So with this, because z is greater than 0, we can say that y, let me transfer here, z is greater than 0. Of course, we can say that y is greater than x. Okay, it's greater than x because z cannot be positive otherwise. Okay, so what does this mean? So it means that if you're going to map this one on as our density function that we had before, it looks like this. This is 0. Okay, then 0 is greater than z, but it is smaller than small z. So if we have this function, for example, then our z, the big Z here, is found in between. And if we're going to go backward, to move backward, it could be that, or it is, the z is between here. So when we have a, let me use another one, another color, so that you could see. So for example, it's like that. So this is the origin, this is 0, and this is the -1, -1, this is +1. So z is somewhere here, and z is somewhere here, if that's positive. But what we are considering is that it is actually lower than 0. We're going to have that one later as we move on, but always remember that z is greater than 0, and because z is greater than 0, therefore y is greater than x. So here y is greater than x. Okay, so with that, we would like to say that we can compute this scenario using this one, the probability measure that z is less than z is equal to the double integral b1, the derivative x and derivative y. So maybe you would ask me, where is this b1 coming from? Okay, remember that we talked about our number line before. So when we studied about the density function, okay, the normal density function, so we actually do like that. Okay, and this is point A and this is point B, remember? And then from here going here, the area is equal to 1. So in this case, we said that y is greater than x, so z is greater than 0. So expressing this in a mathematical expression, we could say that 0 is less than z, such that z is less than z. Okay, so using the integral, we could say that the probability measure that z is less than z is like this. Okay, so with b1, this is actually the interval is 0, from 0 to z. Okay, so this is the situation of our problem. Now, how are we going to translate this interval into an interval relevant to the value of x and y? For 0 is less than z, so we have y. So we have y less than or greater than x. How are we going to do that? So we could say that z is less than z, and then we have y is greater than x, 1 over z plus 1. So putting this together, we can actually put them together, and then we can say that the maximum value of x is x, 1 over z plus 1, which is less than y, which is less than 1. So remember that again, that our value, the perfect value, is 1, so it will never be above 1. So what are we going to do here? So to make things clearer, we're going to integrate the value of y. And how do we do that? Okay, here. So 0 going to 1. Maybe you'd ask me, where is this 1 coming from? Because the value could be from 0 to 1 in our number line, right? So the maximum is x1, that is x 1 over z plus 1, which is less than y less than 1 derivative x. And if we're going to compute this one, then we could get this, which is z. Z is, okay, so z minus x z. This is over z. So in this case, the z here is z is greater than x 1 over x. Okay, so we are not yet over, because we still have to do some kind of integrations for us to completely understand the whole scenario. What are we going to do this? So in this case, we're going to integrate again the value of x, this one. So how are we going to do that? Okay, because remember this, that in our problem z is less than z, and we're going to look for this value. Okay, so what are we going to do now? So we are going to map the distance from 0 to z, because we are really concerned with z. Okay, and now because we found that z is greater than x over 1 over x, then we could say that the integral is from 0 to z 1 plus z. Okay, 1 over z plus, or z over 1 plus z. Okay, so what is this? So this is actually the computation if we would like to get the probability itself, but it has nothing to do with the probability density functions. So what shall we do then? Oh, anyway, if we're going to compute this one, sorry, I forgot. If we're going to compute this, so this is the distance that we're looking for, but then we're going to, I mean, this is the range, okay? So this is the range where we can find the value of z. So what is this? This is from 0 to this point, okay? Z over 1 plus z, okay? Then negative x plus z minus x z over z. Then you could find this one, okay? So, but then again, this one actually computes the probability itself and not the density function. Okay, so what shall we do if we would like to compute for the probability function? Because remember that what we're looking for is what is the probability density function that one, or this one, that f, let me write that down here, f z can be found in this interval. What's the point? Okay, at what point? Okay, so how to do that? Okay, so we're going to do f, this is z, then which is equal to 1 over z plus 1 2. Then z here, z is greater than 0. Okay, so as you could see here, we just actually differentiate the last expression. And so where is that expression? Okay, this expression, all right? And then we do some kind of, differentiation or derivation, and then we got this one. So we differentiate again, just to make it clearer. We differentiate this last expression, then we multiply that by itself, or we just write here times 2. Okay, so that we would be able to get the distance from a 0 going to the -1. So in this case, we've seen that we could not actually use our usual calculus, but the best way to do that is to think beyond the calculus method that we are used to. Why do we have to study this? What is this for? To understand the essence of this topic, let's remember that a function is a special type of relation in which each element of the domain is paired with exactly one element in the range. So with this, you will be able to appreciate the relationship on a continuous scale. Just imagine the effect of a certain saving device to your electricity consumption. It is hard to imagine the exact effect on the consumption without describing a certain range. So after all being said and done, let's try this. How do we translate intervals? How do we translate, or why do we translate intervals? Please write your comment or your answer in the comment below. Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.